Tonight's video lesson is going to continue with our exploration of ionic compounds, and so this is video lesson 2.6 as part of our forensic science unit. My objective for tonight is that you'll be able to write ionic compound formulas involving polyatomic ions, and that you'll be able to write ionic compound formulas involving transition metals. Up until now, and we started this yesterday, we drew Lewis dot structures to show how the valence electrons are moved from the metal to the non-metal to form an ionic compound. And this picture's been time-consuming to draw, and there is a quicker way to do it. And so tonight I'm going to go over that because it's also going to help us with transition metals and polyatomic ions. To begin with, if we take a look at sodium and chlorine from before, we know that sodium has one valence electron and chlorine has 7 valence electrons. And from this drawing we were able to show that we can move one valence electron over with chlorine, and that gives us Na plus 1, and it gives us a chlorine ion that now has a minus 1 charge. Okay. And that's going to tell us that we're going to form NaCl, one atom of sodium, one atom of chlorine. Another way we can look at this, though, is if you know what the charge is for the ion that you're going to be forming, or you can go about figuring out what that charge is going to be, we already know that sodium has a plus 1 charge and chlorine has a minus 1 charge. And what you can do is if we take the sodium charge here without the sign, we can take this down and put it down by the chlorine atom. And if we take chlorine's minus 1 charge without the sign and put that down by sodium, what we end up getting here, we get sodium and it says that we have one atom of that, and then we get chlorine and it says that we have one atom of that. And this will work if you know the charge. You can just take the charge and apply it to the other element involved with your compound, and that's going to be how many you need. So let's do this real quickly for something a little bit larger. Let's say we have aluminum, which is a plus 3, and we have chlorine, which is a minus 1. Now, the chlorine charge here, we're going to ignore the sign and move it down by aluminum. Okay. And what that says is that we're going to need one atom of aluminum. If we then take the charge from aluminum and put that down by chlorine, that says that we need 3 atoms of chlorine. And so my final compound formula is going to be AlCl3. If you were to draw out the Lewis dot diagram, if we were to draw out the Lewis dot structure for this, and we have our 3 valence electrons for aluminum, I could draw in those individual chlorine atoms and demonstrate that it takes 3 chlorine atoms to balance out our 1 aluminum atom. The reason this works, again, is remember we said that Ionic compounds, even though each part has a charge to it, so you'll have a cation and an anion, overall the compound has to have no charge. Right? Now, if we look at the transition metals, which are on page 255 in the orange textbook, these are metals that have more than one charge or that do not follow the valence electron rules already established. So you will need this table on your periodic table. And there are two naming systems that we could use. One is we could use the Roman numerals. And so based on the number of Roman numerals, that indicates its charge. The other way we can do this is by using what's referred to as its classical name. So an IC ending indicates that it's the larger charge. The OUS ending indicates it's a smaller charge. Personally, I find the Roman numerals the easiest way to do this because it automatically tells you the charge. So looking at this, if we were, for example, to take iron 2 ion, okay? What this Roman numeral here indicates is that indicates the charge on our iron. So it would be an Fe plus 2. I could also have written this as ferrous ion, and that would also be an Fe plus 2. But unless you know the charges, the classical names are very difficult to use. So for the most part, I'm going to use the stock name or the Roman numerals as also referred to as. So if we were to do an example with this, if I told you that you were going to have if I told you that we were going to use iron 3 ion and oxygen. Okay. Iron 3 is going to be a positive 3 charge, and we got that because of the Roman numerals. Oxygen, if you know oxygen from before, has a minus 2 charge. Now from this we could go about and draw out the Lewis dot diagram, but I'm going to do the shortcut way. And so the 3 is going to come down here by oxygen, and the 2 is going to come down here by iron. And so that's going to give us a final formula of Fe2O3. If we do the math for this, and let's say we have a positive 3 charge, and we're saying we need 2 atoms of that, okay, that's going to give me a positive 6. At the same time, if I have oxygen with its minus 2 charge, and we're saying we need 3 atoms of oxygen to balance it out, that gives me a minus 6 charge. So 6 minus 6, that equals 0. This is balanced. That's how you work with the transition metals. The polyatomic ions work in a similar fashion, except for now what we're dealing with, instead of dealing with things that have multiple charges, we're talking about ions that are composed of multiple elements. So the majority of these are going to be anions, and they're found on table 9.3 on page 257. But they have a set composition and they have a set charge. Some examples of this that you may have heard of before include like cyanide, which is always going to be Cn, and it has a minus 1 charge. Other examples that you may have heard from before or heard of before would be like phosphate, which is always going to be PO4 minus 3. Now, I'm not expecting you to memorize this chart, but you should know how to use it. And if we know the charge for our polyatomic ions, just like with the transition metals, we can do the math and we can figure out exactly what our compound formula is going to be. So for example, for a polyatomic ion here, if I give you lithium and cyanide, we know that lithium has a +1 charge and cyanide has a -1 charge. And so just like before, I can take the charge from cyanide and the charge from lithium and switch them. And this says that I need 1 atom of lithium and 1 atom of cyanide to form LiCl. If you were to need more than 1 polyatomic ion though, and let's use magnesium and cyanide again here. So magnesium's a +2, cyanide's a -1. And this is a little bit different in that we're still going to switch our charges here and find out that we need 1 magnesium and 2 cyanides. But rather than just write a that we need 2 cyanide polyatomic ions like this, this indicates that I now have 1 magnesium, 1 carbon, 2 nitrogens. That's not right. Okay? Instead, to indicate that you need 2 cyanide ions, we're going to put the whole thing in parentheses and then put a 2 on the outside. This is just like in math when you do the distributive property. So the 2 applies to everything inside, and it functions as a group. We're never going to change how many carbons or how many nitrogens go into cyanide. For tomorrow, what I'd like you to do is I'd like you to be able to come in with the note guide complete. We're going to do a lot of practice with this. I know it's a lot, and you'll do just fine with it. Thanks for watching. Have a wonderful evening.